Okay, everybody, welcome to the fourth lesson in our statistics playlist. This time we'll talk about the standard normal distribution. So we've been, building this idea of a bell curve, a normal distribution over the past few videos. And we talked a little bit in the last one about what a z-score is, and how it was a way for us to take any set of data, standardize it as being specific intervals away from a central point, and we call that our average or the mean. Now we can do all of these things again with respect to the area underneath that curve. In other words, the probability. So if you remember from the last few videos that a standard normal distribution has the following properties, and they are an average of 0, standard deviation of 1, and any z-scores to the left of the average were below, in other words, they were negative, or any z-scores to the right of the average were positive, right? I could separate my positive and negative values as being up either above or below the mean. And we had a formula to do that where it said the z-score was, a specific value, a specific data point you were looking at. We called it x. We subtracted out what the average was and divided it by that standard deviation to figure out exactly how far away from the average it was. Now, when those z-scores are known, both the upper and lower ones, right, the boundaries, the probability can be calculated using our normal CDF function on the calculator. Really, this stands for the normal cumulative distribution function. So all it really does is give us the probability that, data will lie in a certain boundary. So it's very, very similar to when we did quadratics and we defined the left and right boundaries in order to find a vertex or a 0 or something. We can define those left and right boundaries here. There just happen to be z-scores, and the number we'll get out of this is the probability that a specific data value will lie in between those two boundary points. So here's the steps to do this on the calculator. We'll hit second and then the vars button, right? Second and the variables button. It'll get us into that distribution menu up in blue up in the top. And I'll show you what it looks like. So second vars to get that distribution menu, and there it is. Normal CDF is option number 2. Okay, we won't use option number 1. It'll stand for a probability density function, which we aren't going to go calculate. Really just we need the cumulative distribution function, number 2. Now, once that is selected, we're going to have to enter some information into our calculator. And this is the specific order that it has to go in. I can't put the numbers in any other way, or else it won't tell me what I'm looking for. So if I were to press normal CDF on my calculator, it gives me just a set of brackets, and it's blank. And this is the order your calculator wants those numbers in. So the lower boundary separated by a comma, then the upper boundary, the average, and lastly the standard deviation. Again, all 4 numbers should be separated by a comma. Some calculators will actually have them listed out, and you don't have to separate them by a comma. This model just doesn't. So if yours does, great. If not, just follow this pattern. And remember, if you're entering z-scores for lower and upper boundaries, enter a mean of 0 and a standard deviation of 1. These boundaries don't need to be z-scores. They can be specific values with respect to the question. But if you are given a standard normal distribution, z-scores will work. And just remember that if you're using z-scores, it's a standardized way of looking at that bell curve, so the average should be 0 and the standard deviation should be 1. Now, for lower boundaries that go on to negative infinity, because this is the one thing we haven't talked about just yet, the bell curves really extend in both directions forever. Right? I can't really touch that x-axis or go past it, which means they extend infinitely in both directions. So if it's a boundary that goes to negative infinity, this is what we'll enter into our calculator. -1, with that e there, it really is just saying this in scientific notation, where this just stands for -1 times 10 to the power of 99. Okay, so a really, really, really big negative number. Okay, that's the best approximation we can make with the calculator. For an upper boundary that goes to positive infinity, it's the exact same thing, just instead of -1, it's +1. Okay, so a really, really large positive number instead. Okay, and then that E is located right above our comma. So I have to press the second function to get the e's in there. That's how I would do scientific notation on here. So for example, if I did 2 times 10 to the power of 2, this should tell me it's 200. Which there it is. So I know the scientific notation works out. It's just second and then the comma button to get the E in there, okay? So 1 and then second comma for the E, 99. Now, it's not going to tell me what that number is because there's way too many zeros. There's 99 zeros after it. Just way too large. Okay, so our calculator will deal with the approximation. Okay, so let's go see how we can actually use this to, help us, determine what we're looking for. So determine the area underneath the standard normal distribution curve for each of the following boundaries correct to the nearest 10,000th, 4 decimal places. Usually that's where we're going to go for probabilities. So if this is a standard curve, I'm looking for the probability, so the area underneath it. I know that I'm given a z-score. Right, and that z-score that I care about, the boundary, is 0.9. So I know the average is 0 if this is a z-score. So 0.9 must just be above it somewhere. So it's just a rough estimate. There's my z-score of 0.9. Now my inequality symbol says I want to be anything greater than 0.09. So I'm going to shade in the region of this curve that's greater. Right, everything to the right of this 0.9 z-score is what I really care about, right? That area underneath. So when we go to do this, really I need my calculator. There's no way to do this by hand for us. So in my calculator, we're going to go normal, C, D, F, and we're going to place in 4 numbers. Lower boundary, upper boundary, mean, and standard deviation. Now when I think about the lower boundary here, think about what I just shaded in. The lowest possible z-score that I could have, 0.9. That's my lower boundary. The smallest z-score on this purple shaded region. Now the biggest z-score I could have, well, I know that this bell curve extends forever, right? It continues going in this direction and it doesn't stop. It just gets infinitely close to this axis line. So this is where I'm going to use infinity. And the way I can represent infinity in my calculator is 1 times 10 to the power of 99. And make sure it's positive because I'm going to the right. Now I need a mean, and if it's a z-score scenario, I'm using an average of 0, standard deviation of 1. So these are the 4 numbers that I have. So second vars, normal CDF is option 2. So 0.9 is my lower boundary. Upper boundary is that infinity number. 0 is the mean, 1 is the standard deviation. I can close the bracket and then hit enter. And here is the number that I am told. So my probability, so let's say probability equals 4 decimal places, so 0.1841. Okay, so for whatever this situation is, there is a probability of about 18% that whatever I choose will be to the right of the z-score of 0.9, right? Which must mean all of the area to the left of that, right? So everything I just colored it in pink here has to make up my 100% probability. So I could find out what that is pretty easily if I do 1, which is the total, and subtract the probability that I know, 0.1841. I know everything in pink then, all of the other stuff. This should tell me that 81.59% of data lies in that pink region, because I know that 18.41% must lie in the purple. In total, they have to add up to my 100%. So really it's just us determining probability. If a given event is going to land with a standard deviation value bigger than 0.9, a z-score value of 0.9 or larger or less, right? It's just going to tell me where that event is going to lie. Okay, we can try this again with B here, and really all it does is change the z-score value. So again, it's still a z-score, so the average is 0. A z-score that's negative happens to the left of that average. So it doesn't really matter where you draw it. It's just really is a placeholder, so negative 0.6. And I want everything, again, that's to the left of negative 0.6 because this says my z-score should be less than that. So the region I care about is everything to the left of negative 0.6. So if we go to fill in all the things we need, there's normal CDF, lower boundary, upper boundary, mean, standard deviation. Now, this time, since I'm everything on the left of this, I know this is going to continue on forever. So it's going to go all the way this time to negative infinity. Previously, the last one went to positive infinity. Now, the smaller number between the two, the smaller value between negative infinity and negative 0.6, well, the smaller value is negative infinity. It's just a more negative quantity. So negative 1, E99. That is my lower boundary this time. The biggest value I could have in this shaded region is negative 0.6. So negative 0.6, mean of 0, standard deviation of 1. So there are my 4 values that I need to plug in. So second bars again, option 2, negative 1, E99, negative 0.6, 0, and 1. Okay, so there we go. So I know my probability is 0.2743, or in other words, that is 27.43%. So you could see it written as a decimal, you could see it as a percentage, you just need to know how to convert between the two, right? So if I take 0.2743, I can multiply it by 100 to turn it into a percentage, right? That's how I got that value. Okay, so if that's 27%, I must know then if I do 100% and subtract the percentage I know, that means the other side of this bell curve, all of the other part I don't know yet, right, that should account for the rest. So that's 72.57%, and the part we just calculated, 27.43%. Right? In total, that should make up my 100. Okay, so really we're just looking for the probability that a certain event will land within that range. Okay, sometimes you're not given specific values, however. So for C, we got to do a little bit of decoding here to figure out what we're asked for. So again, I can assume this is a standard normal distribution, so I can put my average in the middle of 0. Now, if I take the average and I add on to it 1 standard deviation, if this is a standard normal distribution, that means I'm at a z-score of 1, right? 1 value or 1 standard deviation above my average. And if I do, the average minus a standard deviation, well, that must mean that I'm at a z-score of -1. I'm below the average at that point. So if I'm looking for, the probability that I'm between those two values, right, there's my boundary this time. Right, there's the region in purple that we care about. So the lower one is the smaller value. The upper is the bigger z-score value. So I'm going to do this the same way. Normal CDF. Oh, excuse me. And then if I throw all my numbers into there, well, it's the same 4, right? I'm looking for the lower boundary, the upper boundary, standard deviation, and mean. So in the correct order then, lower boundary first, so -1. Upper boundary of 1, mean of 0, standard deviation of 1. So we'll do this the same way. So throwing all those numbers in there, normal CDF, -1 is my lower boundary, 1 is the upper, 0 is the mean, 1 the standard deviation. Close it. Now, We said in a previous video that if I'm in between one standard deviation above and below the mean, well, the probability that something lands in there should be 68%. So before I even hit enter, I should know that that's the number I'm going to see, right? And there it is. So we're just rounding it for ease when we say 68%. But really, if I go to 4 decimal places, this is going to tell us the probability. Can't spell this word. Probability is, or should be, 0.6827, or 68.27%, right? Which is something we actually learned a few videos back, that if I'm in between one standard deviation above and below, 68% of all data will be in that range, right? Which is the expected value we should have gotten. So this must mean then that if I do 100 minus 68.27, I have 31.73% left on, left to deal with. So it's equally split. So I have 15.865% on each side of that purple boundary. It gets further split. So if I were to do this again with 2 standard deviations, which I can try, right? If I was within 2 standard deviations instead, I should have 95%, and there's the value. If I did this with 3, I would have 99, and you would see that number come up as well. Okay, so D is the same, except I'm in between, 2 different values now. So it looks a little bit cryptic, but again, if you remember this as being a standard distribution, if the average is 0, really I'm, 1.6 deviations above the mean, which really just means I am, well, here's 1.6, and if I'm 1.8, I'm just a little bit above that, right? And I can determine what these z-scores are going to be. So if it's the z-score I'm looking for, it'll be whatever the average is, which in terms of a normal standard distribution, the average is 0, plus 1.6 and the standard deviation of 1. So one of my z-scores is 1.6. And if I do the same thing for the other side, that's z-score 1, let's say, this would be z-score 2. 0 plus 1.8 multiplied with 1, so the second z-score is 1.8. Okay, so there's the 2 numbers. Now if I'm looking for anything in between there, well, again, there in red is the boundary I care about. So I know it's going to be very small when I find this probability. So normal CDF, a lower boundary of 1.6, an upper boundary of 1.8, an average of 0, a deviation of 1. Okay, so same thing. Plug them back in. 1.6, 1.8, 0, and 1. Okay, so very, very small probability this time. So the probability is 0.0189, I guess we'll go with. Or, let's turn that into a percent, so 1.89%. Okay, so really, really small chance that one of our data values picked at random will fall into this specific boundary, right? Which makes sense. It's a really, really small, difference between those z-scores. Now, what happens if you actually know the probability that you're looking for? Actually, sorry, let me reword that. What happens when you actually are given a probability and asked to determine what z-score makes it happen? Right? There's a way I can work backwards here also. So if I'm given the probability or the area that lies below a particular boundary, the boundary value can be determined using the inverse normal function. So essentially this is like doing the opposite of what we just did. And if you press second bars again, you'll see that option there, inverse normal, is number 3. Okay, and again, it's going to ask you for some specific numbers to get put in. And this time you only need 3 values. right? The area that's to the left of the boundary, that's key. Has to be the area on the left side. And then the mean and the standard deviation, right? That really is all I need. Now, if you want the boundary expressed as a z-score, enter the average as 0, the standard deviation as 1. If you don't enter those and you enter in specific contextual things, the value you get out of it will be a specific value relating to the question. It won't be a z-score anymore. Okay. So for each of the following curves, determine the z-scores to the nearest hundredth that make it possible. So I've got an area shaded underneath this curve. It's given to me as a decimal, right? 0.65, that's my area. The z-score I'm looking for is the boundary that makes this happen. So here's the z-score that we're trying to find. So in terms of doing this with that inverse normal function, we need 3 values, right? The area that's to the left of that boundary, which I have, it's 0.65. The average and the standard deviation. Since I want this as a z-score, average has to be 0 for a standard curve. And again, of a standard curve, the deviation is going to be 1. Okay, so we can put those numbers in. So second vars, option 3, 0.65. 0 is the mean, 1 is the deviation. Enter. So the z-score happens to be just past 0, and it works out to be to the nearest hundredth 0.39. So there's my z-score. Okay, so really, really nice. As long as I know what those 3 values happen to be, I can find the z-score that makes it happen. Okay, and I could double check this as well if I use now the normal CDF function. Again, I need the lower boundary, upper boundaries, average, standard deviation, and I know what area I'm supposed to get this time, right? I know my probability is supposed to be 65%, so my lower boundary is that negative infinity number. Oops, that's E99. Upper boundary should be the z-score we just found to check if it's right, so 0.39. Average is 0, deviation of 1. There's my 65. Now it doesn't look exactly the same. It's because we've rounded throughout, but I still have that 65% as needed. So I know it does work. B, however, is slightly different. So I'm still looking for this z-score boundary, except there's one issue. I need to have the area that's to the left of it. Right now I know the area to the right. Now if I know the area to the right is 0.2, the total area must be 1, so the area that's on the right side has to be 0.8 to make this possible. So I have to use 0.8 to do this, not 0.2. If I did use 0.2, what it would tell me, or what I'm telling my calculator, is that this part is 0.2, and it would give me actually this z-score on the left, not the one I'm actually looking for. Okay, so I gotta really, really be careful what area we're using. Always to the left of the boundary. Okay, so here's my inverse normal, and we're gonna put in the area on the left, which is 0.8, mean of 0, deviation of 1. So second vars 3, 0.8, 0, and 1. And there's my z-score, which makes sense, right? It should be to the right of 0, 0.84. Right, if you got a z-score that was negative here, that should be a very big giveaway that you did something incorrectly, because with where your z-score is located in the picture, it's on the right side of 0. Okay, so that's a nice double check in there too. Okay, brings us to the end of finding those probabilities and using them to, determine z-scores, all that stuff, which we'll put all this together in the next one when we start to talk about the applications. So I know there weren't too many word problems in here, so we're just trying to keep them separate. So the next one we'll have a bunch of applications and word problems. So look out for that linked above, and we'll see you next time.